if we want to ask about the equivalence of two containers, the equality of two containers, we might naively think that the equality of two containers is just going to check, are these containers the same length? And if so, are each of the subsequent values inside these containers equivalent to each other? And this might be our implementation for equality in pure Python to match what equality on a list looks like at the C layer. However, there is a performance optimization that has been added to list where what will happen is in the PyObject list, or in the PyList object rather, we'll first fast forward to the first entry that is not identical and then check that on equality. And so we may naively think that our previous implementation will work, but if we put a non-reflexively equivalent object in our list, like a float nan, in our implementation, it will say they are not equivalent because nan is not equal to anything, not even itself. But in the actual implementation, it'll say they are equivalent. And so what you can think is there's one extra clause here for list equality. This means that lists actually behave materially different than NumPy and D arrays, because on a NumPy and D array, a NumPy and D array with a nan in it will never be equal to another NumPy and D array with a nan in it, because that'll be a broadcasted operation. You'll get true, 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 and then a false. And if you look at all of those values using your reducer, your any or all, you'll see here with the all that they're not all equal. The z doesn't equal the z in one case, whereas the two lists are equal. This is yet another subtle difference between lists and NumPy and D arrays, but it kind of makes sense in terms of what we do with the NumPy and D array and what we do with the Python list. For a NumPy and D array, we're often representing values that we're going to perform some computation on, so it might be valuable for us to do that broadcasted operation to see are all the values equivalent to each other in whatever terms they mean, in whatever way they implement what that equivalence is. Where the Python list, we're often saying, here's a bunch of things that we're going to process. So if we're processing the same identical thing, that they're strictly not equal may not be that important. And as a consequence, we might further bifurcate the usage of the Python list from the NumPy and D array. So why should I care? Well, in truth, identity and equality doesn't really come up when we're first learning Python. It might come up as just an informational thing, and it might come up as just a cute, look at the ID here and look at how interning works, and just see that Python's a little bit more complicated than you might think. However, knowing about identity and equality is critical to debugging. It is often the case that when you see spooky action at a distance in Python, you may need to identify, are these identical objects where if I mutate it here, it's getting mutated there or not? And this may be why knowledge of identity and equality will prove invaluable for you, not necessarily for designing your programs, but for debugging them when something goes wrong. Let's talk about the difference between live views and snapshots and why this matters. When we talk about a snapshot, what we're talking about is some static copy, some point-in-time copy of some data. And when we talk about a live view, what we're talking about is a dynamic, live, updating reference to some data, to some state. And so here you can see that y's is a copy of x's. Well, if I make a mutation to x's, I would not anticipate to see it on y's. It was a copy. It was a point-in-time copy. And depending on when I took the copy, well, that's going to determine which of these mutations I will see or not, because I'm just taking a snapshot of this data. If y's is a reference to x's, if y's and x's are identical, then no matter when I perform one of these manipulations, I will always see that on y's. You can think of y's as a reference to x's. It's a live view of x's. As x's change, whatever you see on y's will change correspondingly. It is not the case that one of these is correct and the other is incorrect, but instead there are circumstances where we want one and circumstances where we want the other. For example, if we have some system that is modeling the employees of a company, we might have our employee database with information about the employees, like their role and their salaries. And we may have some information that we capture, like their permissions that they have. Are they able to access a resource or not? And we have some information about historical bookkeeping. What was our payroll for the year 2020? If you think about it, the entitlements storage should not have a copy of the employee's information. It should have a live reference to the employee's information. Because if Alice happens to get promoted, if we look at Alice via this piece of data, we want it to represent what the actual live up-to-date value is. We want this to be a single source of truth for all live views of the data. However, for the payroll, if Alice gets promoted and our salary increases, well, that didn't really change our payroll for 2020 because that's in the past. And so we'd want this here to be a copy so that it never changes, even if the underlying data changes, because it's representing a historical record of what happened at a certain point in time, a snapshot of a point in time. It is not the case that snapshots are correct and live views are incorrect or vice versa, but the circumstances under which we need each of them is something that we should carefully deliberate. Note that we can make copies both implicitly or explicitly through a number of different ways. For example, if we use our unpacking syntax here, that's going to make a shallow copy of x's. Just as if we use our value constructor here, that'll also make a shallow copy of x's. If we do a dot copy, well, it's going to make a shallow copy of x's. If we use copy.copy, that's going to make a shallow copy of x's. All of these are different ways that we can make a copy of x's, and if we're not eagle-eyed to spot them, it might be easy for us to accidentally not spot that now x's and y's are no longer connected to each other as they would be if we had some code that looked like this. Now, when we're making copies, we oftentimes want to distinguish between a shallow copy and a deep copy. A shallow copy means we've only copied the outermost level of some nested container, whereas a deep copy means we've copied all the levels of a container. Of course, if that container is not nested at all, if it's only one level deep, there won't be a meaningful difference between a shallow and a deep copy. It's only the case if it's a container that contains other mutable things, like other containers or mutable objects. Here, we have a shallow copy of x's, which means one of the two mutations we can perform, inserting a 0 to the first element here, will be visible on both x's and y's, but the other mutation that we perform, appending an element to the end, will not be visible on y's. This is because the copy is going to copy a reference to each one of these initial lists, which means this is going to mutate the copy of that list here, but the shallow copy is going to not copy or it's not going to be a live view of the outermost, the most superficial layer of x's. And so if we append extra elements to x's, well, they're not going to appear in y's. In fact, we can make a deep copy of x's, in which case both of these manipulations will not be visible on y's. No matter how deep we go into this structure and perform a manipulation, it will no longer be visible. What deep copy is going to do is it's going to recursively traverse this structure until it finds immutable objects, and it's going to perform copies all the way down, and so that we've completely disconnected x's and y's. Shallow copies and deep copies are a big source of bugs in actual code. If somebody intended to make a deep copy, to unlink two pieces of data to get a real snapshot, but instead they only made a shallow copy, well, it could very well be the case that these two things are still linked and a mutation through one will be visible on the other. Note that there is some asymmetry. If we think about these two manipulations and we think about whether those manipulations are visible or not, if we have just a reference, y's equals x's, both manipulations will be visible. If we have a shallow copy, one of the manipulations will be visible. If we have a deep copy, neither of the manipulations will be visible, but it is not possible for us to make the shallower manipulation visible and the deeper manipulation not visible. In other words, there's no way for us to make this invisible and this visible. We can only make this visible and this invisible. And so there's an asymmetry here. We're missing an entry. This entry here simply does not exist and cannot exist. Now, note that a lot of things in Python will give you live views, and you should be aware of them. And there may be some subtleties in your code. For example, historically in Python 2, the dot keys gave you a snapshot of the keys of the dictionary, and you need to use a dot view keys to get a live view of those keys. Whereas in Python 3, dot keys is a live view, which means if I add a key in after capturing dot keys, I'll see that key when I iterate over dot keys down here. If I wanted a snapshot, then I may need to use something like this extended unpacking syntax to say, give me the keys as they exist at some point in time, such that future manipulations, future addition or removal of keys is no longer visible through this variable called keys. Note that the idea of snapshots and live copies extends beyond just what you might think of as changes to your data. For example, there are different styles with which we can import things in Python. We can say from module import such and such, or we can say import module, module.such and such. And we can refer to these as an early bound versus a late bound approach, where the early bound means give me a snapshot of how the thing looks as of the import line, versus the late bound, give me what the thing looks like as of when I use it. Here, I'm going to use an early binding of cosine, sine, and pi in the math module. Then I'm going to dig into the math module and I'm going to swap what sine and pi are. I'll swap them so that sine is now pi, sine is now cosine, and cosine is now sine. And because I got a snapshot of them as of this line, I got an early bound view. This manipulation will have no effect on subsequent code. However, if I use the dotted lookup is a live view. And so this will say go into the math module as it exists as of this point in time and give me what sine currently is, which means down here when I say go into the math module and give me sine, give me what it currently is, well, it's going to reflect that I've swapped my sine and my cosine. There is a material difference here. It's just that for the most part, we don't really manipulate modules in this way. And so as a consequence, it's unlikely that we'll be able to see a real consequence from this, except for things like, say, sys.path, which is one of the things in a module that we're likely to actually manipulate in our programs fairly commonly. You can think that a lot of this has a close relationship with getAttribute. You can think that there's a difference between doing an object.x to get the live value of an attribute versus x equals object.x, which gets a snapshot of that attribute. And all the same consequences of choosing between object.x or object x equals object.x and then reusing that, all of these apply to any circumstance when you're thinking about snapshots versus live views. There are some subtle implications for what happens when we actually want a live view or when we want a snapshot copy, and how we might accidentally or incidentally get one or the other through the choices that we make in our code. For example, here we have 4 formulations for how we can create a simple class that takes just a bunch of values. And we can pass in some values, and then we can manipulate those values after the fact. And we can see, is that manipulation visible on the instances self.values? If it is, that means that we've implicitly got a live view. If it's not, that means we've gotten a snapshot. And if we go through these examples, it'll be very clear. If we do self.values equals values, then we have a live view. If we do an unpacking into a new list, well, then we have a snapshot. If we do a .copy, we've got a snapshot. And if we send these in via star args and then take those star args, even if we don't put them into a list, if we just leave them in their tuple, that also will be a copy. Here, we are actually implicitly making a copy of the structure that's passed in. And here, we are implicitly not making a copy. Well, the question is, do we want these values to reflect changes that are made on the outside? Oftentimes, no, because that'll lead to code that's very difficult for us to understand. And other times, yes, because that may be one way that we inject behavior into this class. And so once we deliberate, do we want a live view or a snapshot? Then we can choose between these options. There are some other slight subtleties between these options. For example, here we get a strict list. Here we get a strict tuple. Here we get a copy of whatever the original structure was, which might be even a set or a dictionary. Additionally, here, actually I think that's pretty much the main point of the difference between these. However, there is another very subtle difference if we think about this not just being a list, but potentially having some other behavior, like a collections.dec with a maximum length. Because we get a strict list here, or a strict tuple here, we will have eliminated the additional behavior of the dec's maximum length. So if we were to do an append in here, in this case we have a tuple, so we can't do an append, but if we were to do an append here, we'll lose the first in, first out structure of that dec because we turned what was passed into us as a dec with some additional behavior associated with it into a strict list. Whereas here we'll actually preserve that behavior, but we'll get a copy of this data. Think about how a collections.default dictionary has some very meaningful custom behavior. If you look something up and it's not present, you get a default value. And is that something that we want our object to be able to make use of or not? If not, then we might want to put this thing into a copy via a syntax that looks like this, maybe with the double star and the curly braces. But if we want to preserve that default dictionary behavior, maybe that's an important thing that somebody needs in order to accomplish a goal, we might want to use the .copy. And if we want changes externally to be visible internally, then we might just use this assignment.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.